in case you didn't hear, I haven't graded your tests. I hope they're good and that you're happy with what you've done. My goal is to get it finished by today, so hopefully you'll see sometime this evening once I've finished all my classes. Probably late evening, to be honest, they take hours, but you'll get your solutions as well, and you'll get your report. So let's get started. We did an intro to dot product. Dot products are in this quarter, this week 7 homework. Just a quick reminder, if you have two vectors u and v, the dot product is described like this. And there's some properties of dot products that are quite helpful. Do you know if the dot product is the number 0, provided u and v are not the 0 vector, which is pretty trivial. If the dot product is 0, then the vectors are orthogonal. And orthogonal is right-angled perpendicular. But we prefer the term orthogonal because it allows us to move into other dimensions and not need to change the name. Secondly, if theta is the angle between these two vectors, then we can use this version of the dot product, that the cosine of theta is u dot v over the magnitude of u times the magnitude of v. And this allows us to get the angle. And the biggest angle you can get between two vectors is 180. If you remember me going like this, right? The two guys down here, right? The two guys pointing that way, right? 180. The smallest angle is obviously 0, and perpendicular doesn't care orientation. Would you agree those two vectors are perpendicular? And if you rotate them, they're still perpendicular, right? So that you don't need to be horizontal and vertical to be perpendicular, right? You can be any rotation you like. And u dot v, the scalar, the dot product, is a scalar itself, which means it is a number. So there's a bunch of questions right at the start that go something like this. Let me bring them up for my own benefit so I can remember how they phrase them. It's loading up as we speak. Right. Helps when you hit the right button. I hit the wrong button. And basically, what combinations make sense. In other words, certain things you can calculate and they make sense, and other things you can't. So let me try and be a little bit more specific. Would you agree that A dot B is a scalar, right? It's a number. It's 0, it's half, it's 42. If you were trying to do the dot product of, say, this, that is doable. Would you agree that CID is just a vector? And then isn't A dot a vector going to exist, right? It's going to be a number, and it means it's going to be a scalar, right? On the other hand, to use their words, this is not meaningful. C dot D, is it not a scalar? But you can't do a dot product of a vector and a number, right? That has no meaning. It wouldn't make sense to say what is 1, 2, 3 dot product with the number 7. You agree? That has no real meaning. I'm not meaning 7 times the vector. That's a different story, right? I'm saying the dot product 7, right? That's different dimensionality, essentially. Would that be meaningful? Would that actually be something you could calculate? What I've just read.
Yes.
Yeah. Would that be a number, a scalar? Wouldn't this be a scalar? Wouldn't this just be like 5 times 7, right? It would exist. Not only would it exist, it would be a scalar. And that's essentially what question 1 is dealing with. Which calculations are meaningful and which ones are not? And if they are meaningful, what do you get when you do them? Right. I think last time, if my memory serves me well, which it doesn't always, didn't we do some calculations of dot products? Didn't we do A dot B with some numbers? Does that seem familiar? Yeah. Okay. Just do one. Suppose A is 1, 3, -1, and B is 0, 5, 3. Then if you're being asked to find the dot product, you just go 1 times 0 plus 3 times 5 plus -1 times 3. And that gets me a 0, a 15, and a -3. So the answer would be 12. Are we comfortable about finding dot products? Right. So that basically gets you through questions 2, 3, 4. Right, let's move on to a version of question 5 now. Right, in question 5, the vector A is P, -P, 6P. And the vector B is 3Q, Q, -Q. We're being asked to calculate the dot product. So it's going to be P times 3Q plus -P times Q plus 6P times -Q. Well, that's 3PQ. Take away a PQ. Take away a 6PQ. What does that get me? 3, 2, -4. Comfortable about that? They could have done a better version of that question, in my opinion. Just changing B a little bit. Darn it in space. I'll try that again. It should be Q's. Right, imagine that was the second vector, and these should all be Q's. I almost did that again. Now the dot product is P times -3Q plus -P times 3Q plus 6P times Q. Why I said I think they could have done a better job in this question is because doesn't this answer end up being 0? What does that tell us about the two vectors A and B then?
They're orthogonal.
Right. And I don't even know what the vectors are in any great detail. Would you agree? P could be 42 or 15 or -7, and Q could be 99 or 3 or 42 or anything else. Yet, surprisingly, don't these two vectors end up being orthogonal? Would you agree? So you might wonder what on earth is happening there. So let me show you some vector algebra. Might convince you why these two are orthogonal. Here is the first one. Do you notice that they all contain a common factor of p? So you can actually pull it out like that. So isn't the vector A just some multiple of the vector 1, negative 1, 6? Would you agree? That vector A is just some multiple p of 1, negative 1, 6, right? Like 5.5. And now if you do the same thing with B, which was negative 3q, 3q, and q, and you pull out q just like a common factor, you get that. Now, isn't this a multiple of the vector 3, 3, 1? So if you can imagine this as being the vector 1, negative 1, 6, and this one here being the vector negative 3, 3, 1, those two are orthogonal. You can check it, but they are. So what happens if you stick a p in front of one and a q in the front of the other? Don't you just make this guy longer and this guy longer? But don't you not change the orientation of the two vectors? Aren't they simply just going to be at right angles to each other, regardless of how long you make the two vectors? Does that convince you that these two guys are actually orthogonal? Kind of interesting. So next question is going to be question 7, question 8. See if there's any more like that. 7 and 8, not much. Let's do 7 as an example of this. You're told the magnitude of vector A is 4, and the magnitude of vector B is 8, and that the angle between the two vectors is 30 degrees, and we're being asked to find the dot product. Well, if you rearrange this guy, the dot product is the length of the vector, A, times the length of the vector B, times the cosine of the angle in between. So it's going to be 4 times 8 times the cosine of 30 degrees. And have you noticed that they don't use radians that much, although they do occasionally, in vectors? It's easier for people to see 30 degrees than it is to see pi upon 6. Problem, we do not want decimals. So 4 times 8 times, what is the exact value of 30 degrees? You didn't think you were going to use any of your trig knowledge, did you? Unit circle, 30 degrees.
Is it root
Root 3/2.
I got pretty confident one, and I think it might be one. Would you agree? Okay, so if you do this guy, you get 16 square root of 3. Okay, let me show you some tricks if you're not good at the unit circle, but you are good at visualizing. There are two triangles, only two, that you need to know if you want to do exact values of the basic standard angles. Standard angles are 30, 45, 60, those kind of things, right? The first triangle is 45 degrees each. And you remember that triangle, 1, 1, root 2. You've seen that guy before? 1, 1, root 2. The other one looks a bit more like this. And this guy's 60 degrees. And this guy is 30 degrees. So this is the triangle that you'll use for sine of 30, tan of 60, and things like that. And in this triangle, we get 1, 2, root 3. I was trying to remember which order 1, 2, 3 goes. Do you notice it's like 1, 2, 3? 1, 1, 2?
Yeah.
Whatever. Now, if you wanted to know, for instance, what the cosine of 30 degrees was, isn't it the adjacent over the hypotenuse? Now, from 30 degrees, isn't the adjacent root 3? And the hypotenuse is 2. Do you see the answer? So if you have these two triangles, you can do any of the standard, cosine of 45, tangent of 30, sine of 60. And if you turn them upside down, don't you also get secant of 60 and secant of 30 and all the other guys? So there's a little trick. If you find it difficult just to memorize the unit circle, you can get these guys.
We actually use very precise blocks that have lengths of or heights of 1, 2, and 3 to do exactly the same thing. They don't have a height of root 3, but they have a height of 3. And you can stack them up on top of each other to get 2 of them. So you can make different size triangles.
And what do you use them for, Tom?
When you set up, say you had something and you wanted to machine it at a 45-degree angle, you would take a block of 1 inch high and you'd put it 1 inch away from something.
Oh, so you'd be creating one of these, but using a block.
You also do it with little round rods that are different heights, different thicknesses. In a thing called a sine vise, because it's the sine of the angle.
Makes sense. Yeah. So this little triangles actually get used. Oh, kind of sad now, because I kind of like that thing. Now it's not so interesting that people use it. You know, my favorite math are the things that people don't use. Now that I found out they've used that, I'm not so happy with it. Okay, let's have a look at the next question if I can. Are you looking at question 9? I'll put those answers away. The damn thing keeps doing that. Stop doing that. What?
You just switch over to my version of the homework and then leave the answers up. It'll be fine.
Okay. Here is question 9. I want to just show you the picture and then I'm going to be creating it on my paper because I need to draw on it and do all sorts of cool stuff. So on the left-hand side, there's a vector pointing downwards, which is called u. On the right-hand side, there's a vector pointing downwards, which is called v. And on the bottom, there's a vector called w, which is pointing from left to right. And we are told that all these vectors are unit vectors. Which is not a lot of information. But evidently,
that gives us the angle of all of the angles in the triangle.
You're right, it does. And we're being asked to find 2 dot products. So let me now return and show you how we can use. You've already picked on, Tim's picked on one of the things already. If we go and look at that information, would you agree that this angle is 60 degrees, that this angle is 60 degrees, and this angle is 60 degrees? And why do I know that? Well, if u, v, and w are unit vectors, doesn't that mean that these lines are all 1 unit long? So haven't we got an equilateral triangle? And that's why they're 60 degrees. So far, so good. Now, if you wanted to find the dot product of u and v, it's going to be the length of u, the magnitude of u, magnitude of v, times the cosine of theta. So it's going to be 1 times 1 times the cosine of 60 degrees. And where's my little triangle gone? If I want to find the cosine of 60 degrees, isn't it adjacent over hypotenuse? And so it's 1 times 1 times a half, and the answer is a half. And we should be quite pleased with ourselves that we got that answer. So danger, Will Robinson. This one is not a half. Well, let's see. It's the length of U, the length of V, the cosine of the angle in between. Now, if we're looking at this guy, U and V, the angle between these two vectors, right, is not 60 degrees. Right, here is U. I'll try and draw them separate from each other, right? U's going this way, right? And W, I should say, is going that way. Right, I've kind of separated them deliberately. If you want to find the angle between two vectors, don't you have to orientate them in such a way that they meet at a point and they both leave away from that point? Won't that therefore represent the angle between these two vectors? Does that make sense? That the angle between U and W is this angle in here. It's essentially the angle that you would get if I draw a W up here. And so the angle we want is this angle between U and W. How big is that angle?
$120.
Great. And 1 times 1 times negative a half, the answer is negative a half. So whenever you are interested in finding an angle between two vectors, will you make sure that they're orientated like this picture? That the two vectors are a version of each, whatever it takes to make it happen, are meeting at a point and they are both leaving away from that point. Does that make sense? Suppose I made U this vector and I made W this vector. Would the angle between them be this angle here, which is 120?
No.
No. Wouldn't I have to draw it something more like this? And would you see in this case, wouldn't it be back to being 60 degrees? So don't just look at the angle in a triangle and say 60, 60, 60, and that's what I'm looking for. Couldn't I,
Wait,
if there,
why wouldn't you be above W?
say again?
Why wouldn't you be above W?
Why wouldn't I be above W?
Like this is,
Oh, you could draw it that way as well, but it'd still be 60 degrees, wouldn't it? Yeah, if I'm
wait,
picking you up right, she's saying, why didn't I draw
no, wouldn't that be
that way?
120?
Well, let's see, U goes this way, W goes that way. Oh, let me draw I've got too many versions of this picture going on, right? So let's call them A and B so I don't get caught up with the letters, right? If we had two vectors pointing that way, and this angle here was 120 degrees, this would not represent the angle between these two vectors. The angle between these two vectors, since they're meeting at a point, would be, well, I'd go one with this one, and oh, there's A going that way, there's B going that way. This particular orientation is 120. Okay, let's change the storyline. Let's make that A and this B 120 degrees, right? In this case, when I draw B down here, A would be here. You just see the angle would be back to being 60 degrees. Right. So to get the angle between two vectors, they must share a common point and they must both leave away from that point. Right. If they're both coming together or one's coming in and one's going out, as we have in these two pictures, don't we have to convert them into a new picture, right, that has the property they're both leaving? Are we good with that question now? Right. Don't get a lot of practice on most of these situations. I think there's only one that looks like 9. Okay, now we're moving into a kind of skill building set of questions. Just doing a quick head count: 10, 11, I believe 12 as well. Next one. Oh, let's do these 3. And we're going to find the angle between 2 vectors. So I'll pick a version of 11. So the vector A is going to be -1, 4, 5. And the vector B is going to be 6, 3, and 1. And they ask for the exact value of theta, and then they ask you for the approximate value of theta. And they want the answer to the nearest degree. But the nearest degree is only going to be for this one, right? Well, if I want to find the angle between them, I find the magnitude of the vectors first. So this one's going to be -1 squared plus a 4 squared plus a 5 squared. It's turning 25, 35, 41, 42, square root of 42. This one is going to be the square root of 6 squared, 3 squared, and 1 squared, which I believe is 36, 46. And we'll find the dot product. In this case, -1 times 6 plus 4 times 3 plus 5 times 1. And what's that? -6 add 12 add 5, which I believe is 11. So the cosine of theta is the dot product divided by the magnitude of A times B. So it's going to be 11 divided by 42 times 46. Ugh, that's ugly. Okay. What can I do in with 42 and 46? I don't know. 42 times 46. So it's 11 over the square root of 1932. So theta will be the inverse cosine of 11 over 1932. Did I make any mistakes with these two numbers? Because none of them look even vaguely good. No. So I guess the answer is just ugly. So the exact value, you're just going to do the inverse cosine of whatever, hopefully much nicer looking fraction than I just got. Now, you want to make sure for the approximate one, and since it's to the nearest degree, that's not too bad. I'm going into mode and I'm making sure I'm in radians. And then I'm going to do inverse cosine of that ugly fraction. 11 divided by the square root of 1932. And I have got to check this.
Wait, didn't it want to integrate?
Yes, and I think I was in degrees. Oh, darn it, in space. I thought I changed it to degrees. My apologies. That is much nicer answer. I make that 76 degrees if you round it up. And I'm about to check right now what they say is. And it is 76 degrees, so I'm good. Well, I kind of knew 1 degree felt bad. And I thought I changed it into degrees, but evidently it was in degrees and I changed it to radians, which wasn't too bright an idea. So I would check that as your first thing if it doesn't match. Am I in degrees or in radians? This is a pretty standard question. Would you agree? Everything's numbers. It's kind of plug and chug, right? Find the magnitudes, get the dot product, stick them all together, inverse cosine. Are we good with that one? Do another one. Kind of screwed that up a little bit. This one is a version of 12. And the vector A is going to be written as 4i take away j plus 8k. And the vector B is going to be hi add 4k. This is just me personally. You do not need to do what I'm about to do. I like to use the component form rather than the ijk. And one of the reasons I like to use the component form is, do you know when you do especially the dot product, isn't there a temptation, if you're like me at least, to forget who goes with who when you do the multiplication? I'm sorely tempted to go 4 times 8, which I shouldn't, right? Whereas if I do it this way, I'm less likely to do that. I don't think the magnitude of the vector is going to cause problems because the formula is the formula, right? And you'll be fine. So magnitude of A is the square root of 4 squared minus 1 squared add 8 squared, which is 16 add 1 add 64, which is 81, which is 9. That's nice. I wasn't expecting that. And the next one, technically it's 0 squared, 8 squared, and 4 squared, which is 64 add 16, which is the square root of 80. Of course, isn't that 16 times 5, which is 4 square root of 5? Now dot product. 4 times 0, negative 1 times 8, 8 times 4, 0, take away 8, add 32, and I believe that is positive 24. So the cosine of theta is the dot product divided by the 2 magnitudes. So it's 24 divided by 9 times 4 root 5. They can cancel and you get 6 over 9 root 5. Any more cancelling possible? What can I do?
Can't the 6 and the 9.
Okay.
Yeah.
You see that earlier really ugly one, this guy here? I wonder if that's got something in it. Let me check something. 1, 9, 32. I think it might divide by 4. So it's actually 2 the square root of 483. What's the other squares I should check? Well, 9, I doubt it, but I'll try it. Nope. 9 doesn't work. What else could I try? Well, it's not going to do 16. It's not going to do 25. It's odd, so it's not going to do 36. Might do 49.
It divides by 12.
Yeah, unfortunately, 12. Oh, 12? But 483 is divided by 12. Or the 1932 is divided by 12. Okay.
Yeah, it is.
Right. Since I've already done the 4, that just leaves 3. Okay, that's as good as that's going to get. So if you wanted to be nitpicky, shouldn't I use that version? Which isn't much of an improvement. On the other hand, would you agree this one came out much nicer because it did simplify? And that's the exact value. And if you want to get the approximate value, we can do that on our calculator. Now that I've got it set up properly as an inverse cosine of 2. I'm about to do, I think, a mistake. No, it is a mistake. But not the one I was attempting to do. Okay. Interesting. Let's do it correctly. 2 divided by, put a bracket round. Ah. Do you notice that I got an answer, but only on the 3rd attempt? Now I'm going to put right below it one of the mistakes I did. What on earth is wrong? That one doesn't work. Show you the one that did work. What was the difference? Did you notice I put brackets around the bottom, the 2 times root 5? If you're doing a calculator and you go 2 divided by 3 times root 5, and you go 2 divided by brackets 3 times root 5, do you know you're not getting the same answer? You're aware of that? Now, in the one I got, didn't the calculator just keep spewing out error? You know, didn't work. Well, that's a good sign. But can you imagine there might be some situations where both numbers work, but one of them's the right answer and the other is the wrong one? So be careful of brackets. I don't know. Some of you look like you're not convinced. Okay. 2 divided by 3 times the square root of 5. And the answer is 1.49. 2 divided by brackets 3 times the square root of 5. Agreed? Can you see why the top one didn't work? There is no angle whose cosine is 1.49, right? But can you imagine there might be a different combination of numbers where one of them is 0.29 and the other's 0.79? Won't you get an angle, but it'll be the wrong one? So that's what I was kind of trying to get to. Be careful with your brackets. Any questions so far? Are we good? This is mostly number crunching. So now we are going to find a version of question 13. And I like question 13 a lot. So 1, 1, 2, 3, 1, 0, 5, 2, -1. And we are going to find imagine this is our 3 triangles. ABC. And we are going to find the angles between them. Now, if we set this up correctly, we should be able to find all 3 angles. As a strategy, the first thing I'm going to do is I'm going to find the vector AB, this one, and the vector AC. Why am I getting AB and AC? Why am I not getting AB and CA, for instance?
They have to
What?
start from the same point.
Right, would you agree that AB and AC are leaving at a point and going away from it? Because couldn't we not accidentally not get the real angle, but the complementary, the supplementary, right? The big version, right? Instead of getting 30 degrees, we could end up with 150 if you're not careful. Now, A to B is basically just 3 take away 1, 1 take away 1, 0 take away 2. Now, AC, 5 take away 1, 2 take away 1, -1 take away 2. Are you comfortable about second X take away first X, second Y take away first Y, second Z take away the first Z? You see, I'm saying, for instance, 5 take away 1 gets me 4, right? Are you comfortable about these two guys? Right. So I want to find their magnitude. So 2, nothing, and 2 gets you the square root of 8, which becomes 2√2. And this one becomes 16, 1, and 9. So that's a square root of 26, which I don't think I can do anything with. And I'm also going to find the dot product. And the dot product of these two vectors is 2 times 4 plus 0 times 1 plus -2 times -3. So that's 8 add 0 add 6. So that's going to be 14. And now I can find the angle for the cosine theta. In this case, it's going to be the dot products of AB and AC divided by the magnitude of AB and AC. This is going to be our last question for today. And this is going to be the cosine of theta. And the dot product is that guy. And it's this guy and this guy. So it's 2√2 times √26. So I'm going to go in my calculator and I'm going to do the angle. And it's going to be the inverse cosine of all of this. I could cancel them down, couldn't I? But since it's going to go into the calculator, I'm just not going to bother. So it's inverse cosine. 14 on the top divided by, do you notice I'm putting my little bracket in to make sure I get the order? And on the bottom, it's going to be 2 times square root of 2 times square root of 24. And I just hit the wrong button there. What did I do wrong? Looks good, actually.
You didn't close the square root of 2 bracket.
Thank you. Okay, that was correct, but what did I not do apart from that? Looks good. Maybe I need another bracket. No. Okay, when in doubt, start again. 14 divided by 2 is that guy. Divided by the square root of 2, which is that guy. Divided by square root of 26. An inverse cosine of 0.970725. That's probably enough. And the answer I get was 13. What do they want? Whole numbers or what? Nearest degree. Okay, so that's about 14 degrees. So what did I do wrong in my combination? Inverse cosine, 14 is good, divided by a bracket, 2 times square root of 2 times square root 24. Close that bracket, so that's everybody happy. Close that bracket and close the inverse cosine bracket. Right, look at that damn thing and tell me what button is wrong. Because I can't see what's wrong. I mean, I got a workaround, but I'd rather avoid the workaround.
Isn't it the square root of 26? I don't know if that makes a difference.
Okay, that won't, well, no. That might make a difference. Yes.
Yay!
Because I don't know why I saw there. Just one number difference. Wow, it is touchy, isn't it? So the moral of that story, Tessa, you get a brownie point for that. Well done. The moral, oh, you want 2, do you? Right, I guess the moral of that story is be careful, which I evidently am not. Okay, so your last name and bye-bye.